Voya is part of the performance construction team with Mitsubishi Electric Trane HVAC US. He's focused on efficient HVAC system design for high-performance residential buildings. He's held various positions in the construction and HVAC industry for the last 20 plus years as a remodeler, HVAC contractor, project manager, as well as in sales. Voya strives to expand his building science knowledge and skills at every opportunity and enjoys sharing that knowledge through hands-on training and mentoring for all levels of building professionals. He hopes to one day see the entire building industry embrace strategic electrification and sustainable building practices for the betterment of our society, increased indoor comfort, and ultimately to help homeowners reduce their monthly energy bills. So really important work, Voya, and please take it away.
Thank you very much, Zach. So I actually come to you guys this morning or this afternoon from the lovely state of Austin, Texas. And yes, I did say state of Austin, Texas. We don't count them as the rest of Texas, unfortunately, because it is Austin. But it is lovely out here. The weather's been great. I've been actually enjoying the Building Science and Beer Symposium for the last 2 days. So for those of you that haven't had the opportunity, if you do see an opportunity to join your Building Science and Beer Symposium events across the US, please do. For our European friends, if you do make your way over and decide to join us, fair warning, we do serve our beer cold. I know that's not something I was used to back home in Europe, but I'm getting used to it now and I kind of quite like it. So let me go ahead and introduce our two next speakers. Sean Daly, who comes to us from New York City. He is the commercial area sales manager for the Mid-Atlantic business unit of Mitsubishi. And then Matt Blocker, who comes to us from Minnesota. He is the senior manager of commercial product development for Mitsubishi. So the QAHV product is really his baby and his brainchild. And I believe we're also joined by George. Is George on with us, Sean, or was he not able to join us?
He's viewing, but he's not going to be presenting. So he'll be a local contact for QAHV in the New York metro area. So we will have his contact information up on one of the contact slides, but it's just Voya, myself, and Matt that will be presenting today.
Outstanding. So you guys can see pictures of the rest of us. George, none of us know what he actually looks like. So in the next slide, we're probably just going to see a picture of a lovely Mitsubishi unit. That is what he goes by. That is what he identifies as, is a Mitsubishi condenser. But yeah, from there on, Sean, take it away with your slide, please.
All right. So hi, everyone. Thank you for the great introduction, Voya. My name is Sean Daly, commercial area manager out of the New York area. And I'm just going to get right into it. And first, we're going to hit on the target applications and usages for our QAHV Heat2O domestic hot water system. So just to right off the bat, this is only for use for domestic hot water applications only. We're not approving this for use in any hydronic heating type applications. So if you look at the bottom pictures in this slide here, and Matt, you can click for some animations. You can see, radiant floor, a typical radiator, hot water coils, or an air handler type of service. None of that is going to be approved to use with our domestic hot water Heat2O heat pump system. We only want to see this applied in a domestic hot water way. So you can see above the type of fixtures that we're looking at when we're talking about domestic hot water system. So sinks, showers, dishwashers, washing machines, that's really what we're looking to supply here, hot water here for. Next, I'm going to talk a little bit about the target building typologies where we want to use this system. This is a commercial system, so it is going to be used on larger scale commercial projects, and multifamily and hotels are a great target type of project to apply this system. We can move on to the next slide. And we also have senior care and correctional facilities that would not be a great target to apply this system. And what do these type of buildings have in common? A lot of showers, a lot of sinks, probably a good amount of dishwashers and a good amount of clothes washers. So you need to have that high domestic hot water usage for it to be a good fit to use the Heat2O QAHV heat pump system. So here's some examples of a not great application of the heat pump or the domestic hot water system. Single family homes, just simply not enough hot water demand. Schools, think about it, you have basic bathrooms, toilets and sinks, but really not a lot of showers, not a lot of washing machines going on. So your domestic hot water usage isn't very high at a school. Same thing with office buildings. No one's taking showers, or for the most part, people aren't taking showers at work. So basically our target applications, high domestic hot water usage, and a somewhat repeatable load profile of that domestic hot water. So you can see the target applications all were dwelling units or residential type applications, whether it be forced with a correctional or voluntary with multifamily. Everyone's going to be in there living, taking showers, cleaning their clothes, cleaning their dishes. So those are the type of projects where we want to see this system apply. And with that, I am going to kick it over to Matt to start getting into the technical details of the system.
So real quick, before we jump into the technical details, just because this is for application, there was actually a couple of questions that popped up. If you want to just touch on those, Sean, so we're not talking about them in the middle of the technical session. Graham asks, how about K-12 schools?
So if there is a specific large domestic hot water requirement for that school, we can certainly take a look at it. But in general, we've found that there just isn't the demand there.
And then the rest of them actually look like they're probably going to be better for the end of the conversation.
Okay.
Okay, well, perfect. Thank you everyone for inviting me to the presentation today. Sorry for some of the technical difficulties here. Always fun when you have multiple screens running, but we are, when we look at our heat pump offering compared to what the market has today, we offer a single pass heat pump. And basically what that means is that it's going to take in that domestic cold water from your main for the building. And in one pass through our heat exchanger, it's going to bring it from, maybe 40, 50, 60 degrees all the way up to your storage temp, 150 plus or 140 plus. So that is one of the main differentiators between our product and some of the others that are available on the market. And because of that, we're able to really keep high COPs with using CO2 as a refrigerant, even at lower ambient temps. So there is some differences as to how each apply, and we'll kind of show you a little bit of that as we go through the slide deck, and then really try to keep a good amount of time at the end for Q&A so that we can really tackle all the questions you guys have. So there are other products on the market that are more of a multi-pass design, and they have their place and purpose, but typically they're going to be less efficient in those colder climate scenarios, and are designed and laid out a little bit different. So we want to talk through and what those key differences are. So if you look at a boiler, which we're all familiar with today, a gas boiler is really a multi-pass type system where it's going to go through that boiler heat exchanger multiple times to get to your storage temp. So really it's a good way to explain what our multi-pass system is for a heat pump as well. Multi-pass is really going to be very similar layout. There's a couple of different things that you do a little bit differently with the tanks, but for all intents and purposes, a multi-pass system is more of a direct, replacement for a boiler, but you do get some inefficiencies in your overall design, due to it. And just so you guys know, we will have a multi-pass product in the future as well that could serve some of those other application needs that were brought up in the chat early here, and we could talk about that some more towards the end if need be. And then the big difference is how you treat a single pass system. So one of the real big keys to a single pass system, which most of the time is always going to be CO2 based for refrigerant, is that you're getting really cold water back to the heat pump and giving it a really high delta T on the heat pump. So where this heat pump or our heat pump is going to be most efficient is where you get that cold 50-degree water back to the heat pump and give it 100-degree delta T leaving to your tanks. So with that, we do have to implement some different strategies on how we keep our storage in the system stratified. So you'll see while we have a same main storage tank here, we also have an addition of what we'll call a swing tank or a maintenance tank. And really what this is to do is to eliminate your recirc water coming back to the system and mixing up your stratification in the main tanks. So, you know, I think there's a misconception out there sometimes that the swing tank is for backup heat or other things like that. It really isn't the purpose. The purpose is really to make sure when we have our recirc loop from the building coming back at, let's say our mixing valve is sending out 120-degree water, our recirc is coming back at 110. We want that to hit the swing tank first so that that's kind of our tank that's moving around in temperature, not our storage tanks. So if we were to bring back that recirc right to the storage tank, we would mix it all up, and essentially we would get a higher entering water temp to our heat pump, which would then have sacrifices in efficiency. So there is a little bit more added steps to designing for a single pass system, but your ultimate end game is a lot better performance and higher efficiency, especially when you get to colder climates. So we've talked about a lot of this throughout that last slide, but when you look at these type of systems, whether it's our single pass system or a multi-pass system that are out there in the market, you really have a whole different concept in how you're designing the system. When a boiler, you have a fairly inexpensive to do M+1 or to make the plant very large to overcome, you know, any unknowns in the building load and things like that. With any of the heat pump systems, because their recovery rates can be a little bit lower, it is really important to look at the storage piece. So just to kind of throw out a rule of thumb, and it's not perfect, obviously don't design by this, but just to give you an idea, if your boiler is typically, let's say, 1 million BTUs, and you would typically have, let's just call it 200 gallons of storage, what we would do is basically flip that on its head. So usually if you look at our heat pumps today, if you were going to take that same 1 million BTUs of plant and try to match that with a heat pump today, it would just be way too expensive. So we really rely on that storage to be able to ride through the peaks and provide a more energy efficient system to the end user. So typically, you know, we're going to see, you know, just because of our average COP and things like that, if we were to take that standard 1 million BTU boiler design, we would probably be about 1/3 of that for the heat pump plant. So it's just a rule of thumb, but it is something that we kind of shoot for, mainly just because storage is more cost effective, but also helps you in different utility situations to look at peak demand and ratchets and stuff like that as you may see fit. So ideally, our system is going to run almost all day, 24/7. So you really want to keep that system running throughout the day as much as possible. So you'll see in some of our sizing tools when we get to the end here, we kind of target 16 hours or more if possible. And really any of your peaks in that are taken up by the tank sizing. So this is what the heat pump looks like. So for anybody that's laid out VRF before, it looks very similar to a standard VRF condensing unit. The main difference is that it has 2 water connections coming out of the front. So it's going to be all refrigeration, all the CO2 refrigeration is contained inside the unit. So there's no field work with that that comes to play. And because of that, there is, and CO2's higher pressures, the main difference, if you look at the unit module compared to a VRF module, is it's a lot heavier. So it's about twice the weight of a comparable VRF outdoor unit. But one of the biggest things for us is pushing towards, you know, some of the climate neutral incentives. So going to a CO2 refrigerant is very beneficial in many different avenues. So GWP of 1, but also allows us to keep that high efficiency and low ambient conditions just because of the operating range. The unit itself can do up to 176-degree water, and ultimately that's depicted by UL right now. You may be able to see us do even higher water temp just based on how codes change with that, but for all parts or intents and purposes, it's going to be hot enough to be able to provide that 176-degree water, actually all the way down to -35 if you needed to. So it is a very impressive heat pump when it comes to its ability to provide that hot water. So just some kind of mile markers as to where our capacities are. So it's 100% heating capacity at 36 degrees and around 50% at our cataloged -13-degree range. But then again, it will have that extended range down to -35 if needed. The unit itself has 3 different modes, but for all intents and purposes of sizing, we size around the 40 kW setting. The other settings are really ambient dependent, and they really are come into play when you start using demand response and some of the utility incentives that can come with that of doing a load up scenario on the system. But for all of our sizing and critical sizing, the 40 kW is what we'll size to. You can do 16 of these units in parallel on a system, so a little over 2 million BTUs. And this is kind of what the breakdown of what the unit looks like internally. So you've got on the right bottom here, you've got your CO2 compressor, which has got some of the same functions and features as our hyperheat equipment today. And then in the middle, you actually have 6 of these gas coolers. So technically it's not a condensing unit. It's because it never condenses that refrigerant. And we'll talk about that a little bit in a couple of the next slides, but basically there's 6 of these gas coolers in series that are in parallel that would be CO2 on one side and your cold water in and hot water out on the other side. And then internally, it also does have a small inverter pump and modulating discharge valve. Basically, what this means is this is what's going to control your leaving water temp. So the one difference between this and maybe VRF will be that while it's an inverter compressor, most of the time it's going to run at 100%. So it really uses the inverter more for soft start purposes and efficiency purposes of the motor. In general, the compressor is going to run at kind of that highest frequency, and the water pump is going to dictate your actual leaving water to the tanks and secondary heat exchanger. So like we talked about, GWP of 1, ozone depletion potential 0. If you look at today using R410A, 2088 for GWP, and then a lot of maybe comparables today. Those multi-pass products are kind of in that transition phase of switching from R134A to a different refrigerant. There's various options out there, but it's still going to be a fairly high GWP. And this is all coming into play as we get closer to some of the GWP regulations to meet below 750 come 2026. So one of the key differences, like I mentioned, is that because this is CO2, this is where we gain our efficiency in the heating side at low ambience. So because of the pressure that we have in the system with it, and because we're above kind of our critical point in our refrigeration diagram, we're actually just doing gas cooling on the top side of that pressure dome, right? So you're looking at out of the compressor, it's going through those 6 gas coolers in parallel, and it's actually in a transcritical state that will help keep your efficiency high throughout that whole process, and that's what really likes that high delta T across the heat exchanger. Here's a picture of what those gas coolers look like. So they are unique and patented as far as how they operate, but if you can kind of think of it, your bigger pipe here on the bottom left, that is your water pipe. So you can kind of think of a water pipe just twisted. And then we wrap around the different capillary tubes for the CO2. And it really helps us get that high efficiency out of the heat exchange, lower pressure drop, but also that turbulent flow throughout the heat exchanger. This is just going to show you a little bit. I think sometimes people get, a little bit timid when it comes to CO2. It's actually a very, common refrigerant we use in the US all the time. But the one thing I wanted to show here is that we do use the same vapor injection that we have for our HyperHeat VRF products. So basically allows us to bring in mixed phase gas to cool the compressor down, allows it to run harder at lower temperatures without damaging the equipment. The other one thing that is good to mention here is the defrost in this system is internal. So it's going to defrost internally and just stop that water circulating pump. So it won't actually defrost against your built up storage tank. It's going to defrost internally through kind of more of a hot gas defrost method and not affect your actual storage temp for that small window of time. So this is really what our system ends up looking like from a schematic view. And this slide I'll take a little bit more time on, but it really kind of breaks down to three major components. So you can see what we'll call the primary side. That is our heat pump with water lines to a raised plate heat exchanger that we use in our configuration, mainly just because of the US water quality. It really is much more beneficial to have an easily cleanable heat exchanger that's low cost in case there was any damage or anything like that in this application. One, because it prevents having to do maintenance on the actual heat pump itself, where that heat exchanger is going to have CO2 on the other side. But two, it will allow us in the near future here to also do glycol on this primary side for all the cold climates that are on the call. It will help us have another option from what we're currently doing is basically heat tracing that piping out to the heat pump. And then next is going to be kind of our secondary side, and this is really where our storage is. So we have basically designed specialized tanks to really take advantage of how we store hot water and make sure that we're getting that coldest water coming back to the heat pump. And basically what we're going to do is just control to make sure that we're hitting 140 plus entering these tanks. And you'll see kind of different scenarios where if there's a demand from the system, the heat pumps will basically send that hot water right out to your mixing valve, essentially. But if you're in a storage mode, it's going to start loading up the storage tanks and filling them backward. And then next is that recirculation side, which is kind of your mixing valve, your recirculation pump, and then that swing or maintenance tank. So really the key here is that we want, right now we're using an electric water heater tank for this. So basically you'll see that your recirc load becomes COP of an electric, but we will have that future multi-pass product that we could also use for this load, as well as other space heating applications and things like that. But it is really important when you're looking at designing these types of systems to really look at how you control your recirc pump. So it's not really beneficial to just run it all the time. Really look at some of the smart pumps that are out there to really control that variably, so you don't have a huge recirc load on the system. And here's just showing it kind of more diagrammatically what we might put on plans. And you will see we're going to make some efforts here to revise this solution a little bit more in the future here to kind of pre-assemble some of these things to make it easier for the plumbing installers. But overall, the concept really stays the same as far as the overall architecture. So how do we control the heat pump? Right now, this is done off of a few different ways, but mainly it's really controlled on sensors in those storage tanks. So right now you have two methods, essentially, a 3-sensor control or 6-sensor control. And for the most part, if you're looking at any of it, you're always turning on the system at one sensor and turning it back off at the other sensor. So if you look at the 3-sensor control, what this basically means is you'll see these are just our names for the sensors, TH15, 16, 17. What this basically means is as your storage tanks deplete, and let's say you get up to like 130 degrees at TH15 here, that's going to be the signal to turn on the heat pump. The heat pump's going to run again, provide as much heat as it can as possible at whatever set point you put it to. And then it's going to run all the way down until your TH17 value then gets to a predefined number. So that might be 135, 140, so have you, right? So these sensors can be placed in any tanks, but typically this TH17 sensor kind of always is closest to the coldest water coming into the system. And then your TH15 and 16 can be spread across tanks as need be. Where kind of the 6 sensor control comes into play is when you have more advanced control scenarios, particularly demand response. So when you've got direct utility engagement and when you're running the heat pumps, same concept applies. It's just 3 more sensors. So you know, you may allow it to ride out or deplete the tanks more and not turn on to a different sensor, or you might you know, turn it on at a different sensor for various different reasons. So the 6 sensor, the only thing to know is it is only if you have 2 main or 2 heat pumps or more. It can't be done on a single heat pump just based on how the wiring works today. But really it just offers you more flexibility of where you turn on or turn off the heat pumps in the system. And that's something we can give you guys assistance with as we go through any designs throughout the marketplace. On top of that, there is kind of those different modes that you can put the system into. So there's actually 3 modes, like I showed before, 40 kW, 50 kW, and 60 kW. Where those really come into play again is those utility demand sequences. So if you want to do a load up event and it's warm enough outside, say above 60 degrees, you can then trigger the system to be a 60 kW system, load up quicker, get more capacity out of it for that maybe hour before you get to your peak, and shut down at the peak. So really these just come into play when you're looking at your different utility methods, and depending on market, you may use them or you may not at the initial launch here. We are providing kind of the whole package for this just because there are a lot of specialty items with it, and you'll see kind of some revisions to that package as well. But basically, look, you know, we have a potable water ECM circulator that's essentially controlling the water flow on the secondary side that's going to the tank. So it's pulling your cold water out of the coldest tank, sending it back out and controlling to make sure we're getting that 140 plus to your storage tanks. Specific heat exchanger that has got a really high thermal length and keeps it to be self-cleaning for the whole as much as the envelope as we can. So that is just something we're providing as part of the package. Some different controls, but one of the other main things is the tanks. So if you look at any of the storage tanks out there in the marketplace today, there's very few that actually meet the needs for a water, you know, this type of single pass heat pump system. And we're going to have a couple different offerings for this. Today we have one, but the biggest key is that on these inlets and outlets of the tanks, there's a baffling or sparge system to reduce the velocity in and out of the tank. And it actually will also turn direction of flow. So instead of having flow coming right down into the tank and mixing, it's going to turn that flow 90 degrees and slow it down so you get the best stratification out of the tank. Right now we have sizes 175, 285, and 500 gallons for the storage tanks, and then 150 to 300 for the swing tanks. Just look, we'll keep on revising this, and I have, you know, more and more of an offering here for flexibilities, you know, as the market needs be. And a lot of these things we talked about really have a play with the utilities. And one of the biggest things that we see across the marketplace is just everybody wants to know how efficient the system is, how it's operating, you know, gain that trust in using a heat pump for hot water, domestic hot water. So what we've developed is a control system that pulls in all that data that we get across the system can send it either to a cloud-based platform, or can also go to your BMS or anything else like that. But it has some of that built-in load shifting, demand response with an easy CTA 2045 compatible plug. It's basically a jack on the side of the cabinet that is common utility plug to be able to plug in their Skycentrics or other module to do direct utility control. So it will provide a lot of monitoring of the whole system, give you some glimpses to how it's running, operating, and also some of the maintenance features as well of the system. So it's definitely a big part of the system to build up this marketplace in the US and really get that confidence ensured with all players. So this just shows you a couple of the different interfaces. So it's going to show you, how each one's running. It actually has some KPIs as well as showing you carbon reduction and different efficiencies on the system, but can be set up to do reporting and, kind of a mini BMS type of metric just for your domestic hot water. So next is really how do you size these systems? So right now we've early on in this, we started working with Ecotope, who is a consultant out of the West Coast that specializes in hot water heat pumps primarily, and they've been working on them in the US for the last 10 years or so. And they have an open software that we're utilizing for sizing really multifamily and any kind of hotel, senior living, those kind of applications that really fit that multifamily look and feel. And it's very simple tool to use. We can walk you guys through it as you go, but it really fits the bill well for those multifamily applications where you just put in number of people, number of apartments, your gallons per person per day estimate, and then as you can see here, it's going to give you an output of, this just shows an example on the bottom of 1,200 gallons and 283 MBH. But what you can do is you get this slider, so you can basically depict how much plant versus storage I want to fit my, my actual mechanic room or my building, right? So you can kind of put some conservative nature in here if you want, or look at really sizing, downsizing the storage as much as you see fit. So. And then what we're doing is then taking those outputs and putting them into our what we call Diamond System Builder, which is our same program we do all of our VRF designs and everything in. And it's going to have all those entry fields for your heating capacity, your storage volume, and really, kind of drive you through the design to get you a scope of material. And really, from that standpoint, it really kind of all encompasses everything through those two softwares. If you do get custom applications, every application isn't going to be multifamily, right? Don't hesitate to reach out to us. If there is a K through 12 or something that has a big domestic water load for whatever reason, we can look at it and work with you guys as far as sizing that up. There's also kind of a custom version of that EcoSizer to look at just how many gallons you draw per hour throughout the day that would build into the same fashion. So right now we are using heat trace for everything on the heat pump, outdoors, any water piping that's outdoors. And then in the near future here, actually next month, we will allow for glycol and do some changes to the heat exchanger, allow for that provision in the system for all different codes and that kind of thing. But essentially you have those two options to protecting that hot water outside. And then, same provisions happen for the heat pump itself. You need to make sure it's above the snow line, have heat trace in the drain pan as well for the defrost sequence. And then just normal rules apply for insulation and that throughout the system. So with that, I'll kind of wrap up my section and go to Q&A. And I will stop sharing here and we can pull anything back up if we need to go over a specific slide that you guys saw.
And our first question comes from John Jensen. So John, would you like to ask it?
Sure. So I was just looking at the three sensors through the tank, and trying to read sort of between the tea leaves of how you had it set up. Is it basically the question is it important to have long runs, or is the system susceptible to short cycling in the way that we know sort of like single speed compressors can be on heating and cooling applications?
Yeah, no, good question. So the system is not made to, you don't want to have a steady flat load throughout the day, right? So that's where some of those applications get kind of weeded out with it. It really is made to have those big peaks and valleys in your load profile. And that's where it does best. And then between that sizing of your heat pump versus the storage is really what kind of is going to depict when you turn on and off that heat pump. So, those tanks, if you can see them, I didn't point it out, but they have multiple thermal well locations on them. And then you can basically move those thermistors to wherever you want in the tanks as well to kind of give you your different trigger points.
That's good, John. Cool. All right. So next up is Marcel Studer. Marcel, you here?
Yes, I'm here. Can you hear me?
Yep.
Great.
Yep.
Thanks,
Loud and
Matt.
clear.
You may have answered my question already with the last comment, but if we have a single family and we have a heated pool or a hot tub, would that system work in combination with providing the hot water for the residents?
Yeah, so there is, right now to start, we want to really focus on, kind of just traditional multifamily scopes. But there is that option to look at some of that, to take, kind of a combined usage of the system to use it for your pool heating and that as well, obviously with a different heat exchanger that's rated for that and that kind of stuff. But really to start, we want to kind of focus more on those core solutions to get it out to the marketplace and get it efficient. And then from there we can definitely dive into more of those other applications, and especially when we bring in the other heat pump as well, the multi-pass type product, that is much more suited for pool heating, and that kind of gives you more flexibility to have a overall hot water plant served off of a heat pump.
Okay, great. Thank you.
Awesome. Thanks, Marcel. Up next is Justin Taylor.
Hi, that was a great presentation. Thank you. So something that we're used to doing is to, doing heat pumps for heating and cooling, to use hydro kits to provide some hot water during the summer. And I'm just wondering, can that be tied into the system?
Yeah, so this has come up already in the marketplace a few times, and ultimately there isn't really a great spot to tie them in, other than potentially looking at the swing tank. So the reason being is if you preheat that water, then you just kind of killed your efficiency on the heat pump. So it's almost like a trade-off, one or the other, right? So where we probably could use them most would be, depending on your recirc temperature and that, there could be some instances where you could kind of tie it in like halfway between, the cold tank and the hottest tank in the system to add some BTUs in, but your real problem ends up coming in of your set point of those, or your ability for a set point of those type of the PWFI heat exchangers being only 113 or so. It really limits your ability of where you can actually get a good approach to get capacity out of it. So I guess long answer, really there's not a good spot for it today. We'll continue to work on different ways to integrate things like that, or solar thermal or things like that too, that would be more poised for that preheating application.
All right. Thanks, Justin. Up next is Scott Kennedy. I think, Scott, you had 3 questions. One of them was answered in chat, so maybe let's focus on the 2 unanswered ones. Thanks.
Yeah, that's fair enough. Actually, I was wondering about whether you have battery backup for the heat tracing within the machine in a cold climate. That being said, if you bring us a glycol option, that becomes redundant. So I'm interested in the glycol option. We've had some discussions about whether if there's a fundamental difference in the way the compressor works once you're working with glycol rather than working with standard water.
Yeah, so this has been a big push of mine as well as others to get to the glycol route. For that very reason is you really need to put your heat trace and that on a UPS or something like that to ride out or generator to ride out a electrical scenario like that. And that's where the glycol can come into play. The factory is approving glycol in December here, but we haven't seen the actual derate tables for it. I don't believe it's going to change any operation. It's just going to be a derate factor that gets associated with it, whether it's 5% or, but the biggest thing there, even though technically we could still get away with the same heat exchanger that we're doing today, it gets a little bit muddy in the codes. So we'll be switching to a double wall heat exchanger, even if you're using food grade glycol, you could still get away with the one we're doing today. It just kind of covers more bases and make sure we have, don't run into any local code issues, because the codes are so different around the country.
Fair enough. I think the rest of my questions have been answered. Thanks, Zach.
Okay, great. Thanks, Scott. Next up is Lisa Harrison.
Okay, great. Hi, thank you. My question is, I live in a small co-op. It's a 10-unit building on the Upper West Side of New York City. And we just did a big transition from oil-fueled boiler steam heat to air source heat pumps. But we are still getting our hot water from the boiler. So we're thinking about getting a heat pump water heater. And I'm wondering if this could be an option for us, or are we too small for you?
Yeah, no, thank you, Lisa. So right now, I guess depending on the unit size, but most likely 10 units would probably be too small for the specific heat pump. You would be probably closer to, a 5 or 7 kW, need for, a similar like heat pump. We will have other heat pumps rolling out. There's actually a residential version of this, or kind of a light commercial version of this that is only 7 kW.
Oh.
But it is a little bit down the future here, so I think it's 2 or 3 years out yet. But we do have many air to water products coming. It's just this is one of our first that we really brought to market. So I think we would, unfortunately have to pass on it just from the size, but we also don't want to have, a heat pump cycling all day long, because of that, right? So.
Right. Okay. Thank you.
Thanks, Lisa. So the next question comes from Mark Friesner, who I think just had to jump off to do another call, but I'm going to ask the question on Mark's behalf. So his question is there a single family residential version of this technology, ideally one that can share the same outdoor unit that is connected to the typical Zuba systems that we're installing more and more of?
So I'm not as familiar with the Zuba system specifically, but there are, like I said, a few different more residential single family style products coming in the future that would be, I know one of them for sure would be kind of like our multi-head smart multi type product that would have the ability to keep cooling and heating on some of those, and then also have the ability to do domestic hot water on the same refrigeration circuits. So those are coming. Just don't have a whole lot of details to share on them at this point. But there is, I will say, there's about 15 different products that are coming for air to water overall. Based on the high demand we're seeing, especially with this product overall as well. So.
Well, that's exciting. Great. Cool. Next up is Andrew Peel.
Oh, okay. Hi. Was wondering, first on the recircuit, it could also apply to space heating. And I know you made that caveat at the beginning, this is not for space heating. But I was wondering if you had a recirc line, and it's coming in at a lower temperature, could you not bring that into the position of the tank, or I guess if you have a series of tanks, such that you're not disrupting the cold water feed. So you're not bringing it into the tank at a cold spot, but something that's more in similar temperature, raising the temperature back up and then recirculating it back into the building.
Yeah, so it's a good question, and we are actually looking at this. So we do have several pilot projects across the country. There's one with the CEC in California that is doing exactly that. If you look at it, it's got a header from the recirc that goes to each tank to allow us to test each one of those scenarios. I think there will be some ability to do that, at least to mitigate, a portion of the recirc possibly, because the recirc load can be a higher load. We just really want to do testing on it first to just see how well that performs without mixing the whole storage system. So it also, obviously depends how many tanks you have in series like that. If you have 6, maybe it's viable. If you have 2, it's probably not as viable, right? So, that will come into play, but it is something we are testing and, could look for, have a future kind of canned solution for that when that does come up, or when we want to really peel off that electric heat usage, right?
Right. And so then I don't know if you're testing this application with the space heating, but in theory, I think you could, but be interesting in your view of for the a space heating application where you do a similar approach.
Yeah, I think the space heating GPMs will end up being too large, that you would probably end up mixing a lot more. But really, we're going to try to differentiate that with that other product more, to really be a space heating product that is that low delta T multipass system. There is some concern if the system, the heat pump right now for the QHV is set up to have kind of an anti-cycle timer. So if it does cycle, like the first cycle, it would, maybe put it 5 minutes out before it can restart. Second one, 10 minutes out, and then eventually it would lock out the system. So, before we get in through all of those different variations, we just want to get the core solution out there first, and then, kind of start working through those different concepts. But right now, we really need to keep it as just domestic hot water heating. And, as we progress through that and other products, we'll, open up some more of those kind of specialized applications with it.
Okay, great. Thank you.
Great. Thanks, Andrew. Hey, Vaughn Piccolo, I see that your hand is up. We've got you in the queue for questions, but did you have a follow-on question for this one? It's particularly, no, your hand went down. Okay. I'll interpret that as that you're good. So next up is Enrique Bueno.
Hi, thank you. A great presentation. I just wonder, since you're having an increased storage capacity, and especially in multifamily, the internal gains are very tricky and very problematic. Have you done any research or any calculation how does increased storage capacity can affect the internal gains?
Yeah, I think, I guess to answer your question, frankly, I have not, no, but the tanks are very high insulation. So they are, the tanks that we have today are R16, and we actually will be adding another option that will be an R30 tank. So it really should mitigate some of any internal gains from that heat source, or, that storage source. But we have also looked at other options too, specifically when it comes to retrofit to, put them in an outdoor enclosure or things like that to get them, kind of out of the envelope, that would also help that scenario. We're going to keep working on different solutions to get to, different various applications like that. But we have seen, plenty of demands for that on the retrofit markets, especially where there just either isn't the space for the storage, or, there's other concerns with, location of piping or elevation or things like that.
Okay, thank you.
Thank you.
All right, great. So next up is Douglas Miller.
I'm here. Hi. Yeah, I thought my question was answered in the chat, but
Okay.
related to radiant flooring. Why is this not applicable, in terms of lower temperatures that are useful for radiant flooring? Why would this not be applicable?
Yeah, so I know it was answered, but I'll answer it again then. It really comes down to it needing a high delta T on the heat exchanger. So radiant floor is typically going to be 10 to 15 degree delta T coming back. And it would just kill our efficiency to the point where, it isn't going to be even all that much better than just doing electric heat, electric boiler or something like that. So for the system to be efficient, it really does need that high delta T. And that's what that other future product will be really geared for, is radiant floor, baseboard, space coils, that kind of stuff, to be able to do a 10 to 15 degree delta T well and still be in a high 3.5 COP.
Okay, fantastic. Douglas, are you good?
I'm good. Yep.
All right, thank you. Great question. Okay, so next we have Umit Surt.
Hi. My question was about the commercialization about this product that goes with New York City electrification. I mean, Ithaca decarbonization. It's a very low global warming potential. We are really looking forward for carbon dioxide refrigerants, in short. And I think George answered me to contact with him directly about it. Earlier, Lisa asked about 10 units. For instance, that's a very good example. I know there's another firm out there have carbon dioxide refrigerant, but I think we would like to see more and more. So there is no question. I'm directly going to call
Enthusiasm. Yes. Yeah. No, I think, no, it's good to voice that. Thank you. Appreciate it. So next up is Susan Rowley. I think that Susan had to leave, but I'm going to ask her question for her. And the question is, what are the maintenance requirements, for example, if in a hard water environment?
Yeah, so, typically what we'll do for all of the, that's one of the main reasons we've added the secondary heat exchanger, is just because of those hard water environments, or, our factory, water restrictions for the main heat exchanger in the heat pump itself is fairly strict. So what we'll typically have for all of those secondary heat exchangers is set up as to be a clean in place heat exchanger. So they are a brazed plate heat exchanger for efficiency reasons and that to be able to get the most out of the system. But then you basically have clean in place valves to be able to back flush that heat exchanger. And just depending on your water hardness and quality would be how regular your PM work would be on that. So going to be kind of similar if you get really hard water for any other devices. Your tanks are going to have anodes in them. Harder the water, worse the water, the more the anodes are going to deplete quicker. So, doing that maintenance overall will be very, water quality dependent. But we do have provisions kind of set up from a service side to be able to easily clean those heat exchangers and that, in the case of hard water.
Okay, fantastic. Thanks, Matt. So Vaughn, you're up.
Well, it seems like you kind of just went over exactly what I was going to ask, which is what does if you could speak a little bit about what the maintenance program actually looks like. Is this an annual clean flush of heat exchangers and storage tanks? Is it water softening with a water softening system that's installed, or could you just talk a little bit about that?
And obviously it's always going to be, location dependent and that kind of stuff, but there are, provisions that you could, look to doing water softening, or, I think in general, what we're going to probably recommend for the get-go is, and I have to look back at the number, but there is on all of our diagrams for how we install that secondary heat exchanger, there is a baseline pressure drop across it, and we're going to be able to look at that and say, if it rises more than this amount, then you should be looking at doing your cleaning, especially for that first year where it's kind of, you know, an unknown time frame. And then from there, you can build out your maintenance, preventive maintenance schedule so that, you know, everything can, you know, kind of flow into a normal path. And same thing with the tanks. You're going to kind of see, you know, the anode life and the clean out and any of that that needs to be done from that aspect. So there's not a hard and fast rule other than we'll have that, you know, kind of rule for that pressure drop across the heat exchanger so that you're writing down your baseline when it's clean, and then, you know, kind of going from there. I think it's like 3 or 4 PSI is where you start looking at, you know, potential cleaning of that heat exchanger.
Well, Vaughn, do you have any other questions, or are you set?
That sounds good. I'm assuming we just hire someone who does typically does boiler maintenance or something like that. Could do this. Is there like ports where you can perform this maintenance? Is that kind of, will that be diagrammed?
Yeah, so all of our we have CAD details for everything as far as multiple scenarios, and it will have your fill valve or your flush valves for those heat exchangers. And you know, it does really depend on the contractor at times, or you know, the maintenance team. Some are not going to be used to doing that. Some, you know, so we will want to kind of investigate that, you know, on a project basis, and you know, maybe it's the in-house staff, or maybe it has to be done externally. You know, depending on the situation. So
cool. Thanks, Vaughn. Thanks, Matt. So I think that John Jensen, you might have another question. If you do, let me know. I'll pause for a moment. And the same is true for Andrew. So I'm not seeing John. So maybe Andrew, do you have another question you wanted to ask?
No, I combined the two into one.
Okay, perfect. Cool. So next up we have Vaibhavi Tambe. I hope I did okay with pronunciation.
Yeah, it was pretty close. Thank you so much.
Thank
you so much for the great presentation. I just wanted to know if there are like any part load curves available for any modeling tool. I mean, are there any resources available on how to model the system and energy simulation tools like eQuest?
Yeah, so we've developed you know, internal tool to model it compared to other systems, but we do have all the full data curves on that that can be provided. So just, you know, reach out and we can get you the data curves and that. It isn't built into any specific modeling program out there, mainly because there isn't an AHRI category for it yet. You know, so there's really no good baseline to, you know, show those performance curves, but we could definitely work through if it is eQuest that you use traditionally. We have a lot of good modeling people on our team that can work through that with you as to modeling it in eQuest.
Sounds good. Thank you so much.
Thank you. All right. So next up we have Drew Moore Hubbard.
Okay, so the only question I had, Matt, was just from a floor space perspective. I work for a modular high-rise construction company, a startup company in New York. We're looking at 30-story modular, you know, multi-residential high-rise. And so the question that I have is just from a basic zoning perspective. You know, every 10 floors we're busting those zones up for hot water heating. What would be your approach to that, and what kind of floor space compromises am I going to have to make from a heat pump perspective versus the traditional just electric hot water storage capacity?
Yeah, so in that scenario, just remind me, what was the overall number of floors, or how many floors total?
Yeah, just like a typical 30-story high-rise apartment building in New York. Okay.
Yeah, so a couple of limiting factors that come in when you get to high rises specifically is water pressure, obviously. So the tanks that we have right now are rated 125 PSI. So that's really what we have to work with in each one of those breakouts. So if you set every 10 floors, that, you know, really keeps you within that regardless. And then we would look at on the heat pump side, there is a limitation of where you can have the heat exchangers, the secondary heat exchangers in relation to the heat pump itself. So it's around 175 or so feet one way. So in some applications, you might find yourself putting all the heat exchangers like at the roof level, and then using the secondary pumps, which have a little bit more horsepower to actually get it down to your storage tanks in each floor. I know that's not necessarily ideal from a modular construction standpoint, but for the most part, you would really just look at how many tanks you need for that system. So if you're looking at multifamily, let's say if I take a multifamily building that's 100 apartments, maybe a typical system for that, just to give you a feel for how big it is, would be probably 1 to probably 2 heat pumps, and then maybe something like 1,000 or 1,500 gallons of storage. So you might have 3 of the 500-gallon tanks, and maybe you split that out across each one of your risers, just depending on how it goes. So really, probably best to try to answer that offline and go more into an application specific discussion. But please reach out to us and we can go through that as to working on your specific application, because I know modular does have its challenges, especially with more of a centralized system like this.
Great. Excellent. Thank you, Drew. So next up is Kurt Hurley.
Oh, thank you, Zach. And I think that my question was probably answered multiple times. I live in a passive house in California, which is a 100-year-old bungalow. And 10 years ago, we put in a triangle tube SME tank in the tank, and we have a gas boiler. And I'm always thinking, how on earth am I going to electrify this and get rid of the tiny amount of gas we use and replace with electricity? So the SME tank, I think it has some rudimentary design components or design approach to stratify, but it's essentially a tank within a tank. And the delta, the ADA efficiency, or the delta T, to try to use this appliance would have the same challenge, in that if at the HRV supply registers, the air is about 100 degrees, and the water that's circulating through the Paul hydronic water to air heat exchangers may be 125 F. The return waters, there's not going to be the delta T there. So I think the same challenge would exist. I'm sorry, it's I'm making a totally selfish thing, but there's some engineering interest in my request. So we have to wait until there's some engineering efforts that would, or an approach or appliance that would be different.
Yeah, so it really would be suited for some of those future products, more on the light commercial residential side. But there will be both products, just so you know. There will be both the high delta T product and the low delta T product. So for California, the low delta T product would probably be sufficient for that 125 degree water temp, and you would just have to mix or have 2 different zones for your space versus domestic side.
So potentially the exterior service water jacket of the SME tank that we have, it's now 10 years old, but maybe has some useful life, maybe another decade, who knows, I'm just guessing. But potentially the 2 zone in the low delta T product offering might, if you somehow segregated those, that might be an approach.
Correct. I think that would have its challenges in other colder climates, but in California, you'd probably have an option there to look at that. So.
Oh, I see. Just to be clear, so if you opted for the low delta T technology itself, and you had 2 zones, if you will, input output for the water. When the ambient temperature is getting colder, the technology itself is more challenged to keep its COP preserved.
Correct. Yeah. So it will be, and to keep the high leaving water temp preserved, right? So
right.
In California, we won't have any issues, but if we take that same conversation to Maine or my great state of Minnesota, we'd have some problems.
So Matt, I'm calling you from the city of Berkeley, and so I'm maybe one of the few people on the call in the government realm and interested in sharing technologies with people that are trying to fuel switch in existing buildings and optimize their designs, their design team having all the tools and information and literacy possible in heat pumps as they go and design a new project. So I'm very interested in the marketplace in Japan, and even, if you would be a little bit unselfish, some of your competitors and some of the technologies and maybe even some of the IP. I mean, you mentioned your patent on the R744 circulation that's a wrap around a high surface area core that the water's going through. What do you see in the next 5 years for technologies that will be able to do the job of what a tankless gas water heater is doing? I mean, this product is often, of course, a really important step forward. But do you think there's going to be more diversity and further R&D? It sounds like with these other two products already, yes. But can you share a little bit more about that?
Yeah. So traditionally, it's one of our, as I was a former salesman for our team as well, but traditionally it was always one of those things that really griped us, and that all these global Mitsubishi brands had every product in the world, right? But we are fastly and rapidly catching up. We're actually going to probably surpass Europe overall for sales soon here as a company. And with that's coming a lot of that, more of that opportunity to bring and be the front of line in the development stages for those products. So I guess I would say overall there is a very wide array of air to water products coming. And in general, there is a very big push towards, either low GWP or even natural refrigerants. So I think one of the things that is a challenge is, getting to some of those natural refrigerants. If you talk about the low delta T scenario, your best refrigerant for that is propane, R90. So it is restricted now in the US for certain volumes and stuff like that, but from an industry, we'll have to get beyond that and put in the proper safety measures to be able to use that in the future. So I do foresee it's going to continually evolve and expand, and there are a lot of good competitors out there that are going to drive it as well. But I think you're going to see overall in multiple products be, the drive towards heat pump, the drive towards, some natural refrigerants or other scenarios like that.
So so two questions. The first one, the most important for all my applicants, one of the challenges with heat pump water heating technology, particularly for retrofitting existing homes, is generally, if we look at the cut sheets for your competitors' tanked heat pump water systems, you have a 10 by 10 square foot area, so that the air surrounding the integrated heat pump on the tank doesn't get too cold. And if you're smaller than that, of course, you're doing a ducted installation, and the best appliance lifetime and efficiency performance would be dual ducted, so there's dedicated supply and exhaust. So of course this adds cost, and that carves out space that the person wants to, say, do in their addition or in their new single family. So in particular with heat pump water heating, there's pushback, and for the sort of vanilla homeowners in engaging with their architect or their designer, that's either the extra cost for the ducted installation or consuming that area is an issue. And so that's why this technology here is really great. So I had a question. Do you require ducted, if the enclosure is less than a certain size, are you also, is there a recommendation for a ducted or dual ducted installation? How does that play out?
So yeah, so one of the benefits of ours is that we can run to really low ambience, and we want the heat pump. We want the heat pump outdoors, right? So it's good to run -35, right? So that's you know, some of the beauty that we're going to take from, you know, a lot of the VRF technology improvements goes right into the air to water improvements. So I mean, you know, I think there's going to be a threshold at some point. It might be, you know, -10 degrees F, you know, 0 degrees or something like that, that it becomes challenging to use the, you know, low delta T, you know, air source heat pumps outdoors. But anything above that, I think is, you know, going to be, you know, essentially fair game to do 100% with that air source heat pump. So
with the CO2, the R744, what I'm hearing is absolutely no, you know, you're not going to require ducted. You can do it outside. That whole problem goes away that I was talking about earlier. So another question.
I'm sorry, Kurt. I'm just gonna. This is fantastic. I don't want to shut down this. I don't want to shut down this dialogue. It's really great. But I also want to just respect. There are two other questions that are in the queue. Would you mind if we could circle back to you after we get to those? So I hope that you'll be able to stay, Kurt, because I really don't.
Of course, yeah. I'll write my last question. I apologize. I did.
No. It's really great. It's great conversation. So, but that said, Matt Justice, if you're available to ask your question, why don't we switch to you for a moment?
Yeah, I'm here. Thank you. I appreciate the presentation. Can you elaborate, Matt, on how the defrost is managed in this machine? I know you mentioned that no chill water is rejected to the hot water loop, but I also didn't see a reversing valve on the diagram that you showed.
Yeah, so maybe best if I share again and go back to that slide here, just to walk through it. Sorry, more technical difficulties. Sorry. All right, so I'm gonna leave it in this view to not screw it up. But so this diagram doesn't show everything in it, but there are a couple more LEVs and expansion valves. So if you look right here, this is our refrigerant to water heat exchanger, the big X that's white here. And what we would do in this scenario is we actually will send the hot gas directly from the compressor. It essentially will open up some different LEVs and close different LEVs that would act kind of similarly to a reversing valve. There is no reversing valve in it, and basically send that hot gas right to the outdoor coil, and then comes back to the heat, to the compressor. So very similar if you've looked at partial defrost or hot gas defrost in a VRF system. It kind of contains it all internally there, and then doesn't have to have your heat exchanger and water pump running to kind of get your defrost done. So because of the temperatures and pressures that the CO2 runs at, the defrost is much quicker than even a VRF system. It's probably in the range of 5 to 7 minutes, in kind of a worst case defrost scenario. But really, if you look at it, it ends up being, you're using your electric of the compressor for your defrost, as well as the, heat rejection, that kind of thing. So, so I can maybe offline send you something that's a little bit more detailed for this diagram, but basically, long story short, you just need to know that it then bypasses the CO2 to water heat exchanger and sends refrigerant to the heat, the outdoor heat pump, and then back to the compressor.
Matt, is this a single circuit machine with a single outdoor coil?
Correct. and then you would have multiple modules, so each module is single circuit, single compressor, single fan, and then you have multiple modules as your load goes, higher from your design.
Matt, can you verify that on our that this operates kind of similar to the defrost cycle on our standard systems, where it never actually goes into full defrost mode. It defrosts section by section by section, so you don't actually lose heating production capacity while it's in defrost.
So you actually, for this system, it isn't kind of that simultaneous defrost like we have available on the VRF that can do circuit by circuit like that. But it would stop your production of heating for that small window of time, and basically stop your water circulation pump and everything going to the tanks, defrost quickly, and then get back into operation. And all that defrost derate is already built into the program, so it's going to tell you, what your defrost derate is and account for that in your overall BTU calculation. So
awesome. That's good to know. Thank you for clarifying that.
Yeah.
All right. Fantastic.
Thanks,
yeah. Thank you. So next up is Mohammed Kashif. Thank you for your patience. Muhammad, are you able to unmute yourself and ask your question? If not, I can ask it on your behalf. Let's see. Let me find it. Okay, so the question is, for domestic use, do you need double wall HX field supplied one?
It's a sorry.
Okay, great. Yes, thank you.
Yeah, for heat exchanger, do you need a double wall heat exchanger, or like single wall can work for your application for domestic use?
Yeah, so right now in our current scenario, if we do just water on that primary loop, or technically if we did food grade propylene in the future, you can utilize a single wall heat exchanger for most codes. I'm not going to say all codes because all are a little bit tricky, but from a UPC code and that kind of thing, it is okay to use that single wall, because the heat exchanger in the heat pump is already a double wall heat exchanger. So you're mitigating that fear of interference with the refrigerant itself. But from all the codes being very different, as we move forward, we will probably ship to a double wall heat exchanger just for making sure we're going to meet any possible code out there without having to have an argument over someone's interpretation of the code, right? So it's one of the challenges always with a new product, when we have a lot of outdated codes and times that aren't based on the same technology. It definitely can make it challenging. So long story short, no, you don't have to, but we'll probably go to one just to make sure everybody's needs are met across the country.
Thank you.
Great. Thanks, Mohammed. Okay, up next is Carl Hurahan.
Thanks. So you mentioned 10 units in a multifamily building is too small, but is there a lower threshold of where you would say this is fine, or at least a threshold where you wouldn't have to look at what the existing DHW usage is before determining that this is a good application?
Yeah, so obviously everything's a little bit different, just depending on the application, but what I would look at it, the best way for me to interpret it is look at your market. So let's just say, what market are you from, Carl, just for reference?
Yeah, so I'm out of New York City, but I deal with anything from 2-family apartment buildings to 300.
Okay, so let's say New York City, our typical D rate at, let's just call it 10 degrees or 5 degrees, is going to be somewhere, 60% capacity. So I would look at, is my overall load, above, let's just say 25 kW or above for our heat pump, right? Because that's what we would size it on our peak winter design, right? So if you're looking at just like, is there a good rule of thumb number of multifamily that it starts becoming applied on. It's really hard to say, and depends on the use rate of that multifamily, whether it's low income, and some of that tends to, be more viable. But really you want to just look at what is our overall load and probably look at it in that case to say, you want your heat pump system to be above 25 kW or so, which might end up being more like, anywhere from 25 or 40 apartments and higher, that you're really going to look at this type of system.
Okay, great, thanks.
Thank you, Carl. Okay, so we're going to circle now back to Kurt, and I just want to let people know that if you have any other questions, now's the time. I think once we're wrapped up with Kurt, we're going to let our guests from Mitsubishi Electric Trane HVAC US get back to their day. This has really been fantastic. So type your question in chat now. And Kurt, I think you had some follow-up stuff.
No, I was just interested. I'm not a engineer working on these prototypes with all the amazing technology that that we didn't have 5-7 years ago. So back to the products that are now being, or maybe they're already being sold domestically in Japan, or products that there are now beta versions that are being tested for the low delta T. I was curious, we have refrigeration technologies for small and medium-sized refrigerators that avoid the use of R410A and substitute for that another small chain hydrocarbon you mentioned earlier, propane, but the isobutane R600 is used. Actually, the little dwelling unit I live in Berkeley during the week has, I'm not going to mention their name, but they sell the R600 refrigerators in several sizes. So I was just wondering, is that something that's also being looked at, or just not suitable for this type of air source heat pump?
Yeah, so right now, to my knowledge, we haven't used it in any of our products globally. Not to say it can't be, but I'd have to really look at the psychrometrics a little bit more on that to see, what that would mean or the impact. My gut tells me that it probably is an efficiency thing, not that it can't be used, but it wouldn't provide as much efficiency as another alternate. So propane or R290 is a good solution. There are also various other A2Ls that we are using globally. So R454B, R454C, I've seen 513A. There's a lot of different refrigerants out there that could be suitable for it. But for example, the low delta T product that we are going to roll out will be an A2L, or at least commercial product. I haven't confirmed on the residential product or light commercial ones, but it will be R454C, which has very similar properties to propane overall when it comes to heating and air to water heating specifically. But it is an A2L versus an A3. So that's, the one advantage of it today is it can be applied in our local codes, in the near future here, where the A3s are still, really based in the US on, refrigeration rack systems where it's 150 grams or less is the maximum charge you can have in the system, where from my standpoint, that'll be one of my struggles, is to kind of keep working with code officials and that to get that maximum volume up and show that protections are valid to, keep anything from, starting on fire, I guess. But I think that is, when you look at natural refrigerants, you really look at, three main ones, ammonia, CO2, and propane that really come into play. And propane typically is going to be your best for an HFC replacement in a lot of cases. So
propane's GWP is less than 6, something like that.
Yeah, it's around 3. So it's there with
the mass of your refrigerant charge is less than 3 or 4 kilograms for this unit for your CO2.
Yeah, so I think it's around 15 pounds. I'd have to look back at it.
Oh, a little bit,
quickly,
okay.
but it's you know, somewhere in there, 14, 15 pounds.
Great. Well, I don't want to take, I'm sure other people have some good questions, but thank you. It's, you know, just interesting to, it's exciting to see the technology development going on and the new products, the product diversity, as we're thinking about decarbonizing existing buildings and looking at the space constraints. You know, and if we look at the 4 areas where we're fuel switching and clothes drying and cooking food, space conditioning, and water heating. Water heating is potentially one of the most challenging, and as I mentioned earlier, the space issue is. So this is great to see this product, and I'll leave it at that.
Thank you, Kurt. Yeah, thanks a lot, Kurt. And just to piggyback on that, I want to express my appreciation for the innovation that you all are bringing to the marketplace, and it's so critical for this transition that we're wanting to see accelerate to clean buildings. As well as to thank Mitsubishi for your support of the accelerator. I mean, you were one of the first founding sponsors of our work and have been, have sustained our programming and helped us grow. So I just want to give you all a shout out for that support of the accelerator and allowing us to do the work that we do as well. So thank you. I want to also thank, I think we've reached the end of the questions. What an amazing program. We had nearly 200 people take in your presentation, and now we're an hour and a half in and we still have 50 people, absorbing all the Q&A. What a great geek fest. We really appreciate it. Thank you everyone for being here. I want to just pause a moment, and if you have anything else that you'd like to add, Matt, Voya, or Sean, before we close up.
The only thing that I would just kind of like to tack on, and this is not related with the product itself, but more so just to kind of touch up on one of the big questions that we kept getting at FIASCon 2 weeks ago, and that I've also gotten multiple questions at the event that I'm at today, is we hear and we understand the need for this type of product. We hear and understand, and we want this product last year, not 2-3 years, especially residentially. One thing that got brought up by Kimberly that I thought was a very, very good point was that right now it's kind of a perfect storm of things for us wanting to bring this product US stateside. And that perfect storm is the refrigerant change, making us re-list and retest pretty much everything we produce currently, as well as future products. Secondary is the CO2 change. So having to retest all of that equipment to comply with the new standards that are all going in effect next year and within the next 2 years, so that the newer products like this that we're trying to bring in kind of almost have to take the back seat because the UL testing laboratories right now are so backed up that I think, I don't know, Matt, you probably know closer and better than I do, but the last thing that I was hearing is like they're backed up to like 1.5 years out or something crazy, right, for new products.
Yeah, I think that's pretty accurate. Yeah. For
So,
UL, ETL, Intertech.
Yeah. So all of you guys and girls that are excited about this product and really, really want to see it and really want to specify it in your next project, trust me, we want to sell it too.
Yeah, and the only thing I'd add is just thank you for inviting me, and hope we can keep on bringing more and more product here as soon as we can. Believe me, that's our goal, is to push it here as quick as we can, because we see the big movement happening in the marketplace and the need for it. And along with that will come some challenges like codes and different things that we need to work through in the marketplaces. But just know you have our support here to try to get you to the right path, in the overall product and design of your guys' building. So
I'll just add thank everyone for attending and the great questions, and please reach out to us if you want more information on the project or the product, or if you're interested in using it on your project. We're here to help.